Let's take a look now at the idea of a power series. Let's start off with the definition. If x is a variable, then an infinite series that has the form, the sum, n equals 0 to infinity of cn times x to the n, which will actually be equal to c0 plus c1 x to the first plus c2 x cubed plus so forth, is called a power series. More generally, a series that has the form, the sum, n equals 0 to infinity of cn times x minus a to the n, is called a power series. About, or sometimes referred to as simply centered at A. So this is a power series about A or centered at A. You have the x minus A component in there, where A is specifically a constant. Now, if we have a situation that Cn happens to equal 1 for all n, so all those constants out in front of x is actually 1, then the definition of power series simply becomes the sum, n equals 0 to infinity of x to the n, which would be 1 plus x squared plus x cubed plus on out. This is actually what we think of as a geometric series. Now, for this particular geometric series, we know that the geometric series will converge for the absolute value of x less than 1. We know that. Okay? We've shown that before. We proved that before. Now, a power series will have both a radius and an interval of convergence. So for this geometric series that we just defined up here, or that we revisited, and we know that it's going to converge for absolute value of x less than 1, that tells me that my radius, the radius of convergence, will be 1. That comes from right there. And the interval of convergence will be the open interval -1 to 1. Now we should consider, well actually we need to consider the endpoints. We know that's going to converge on this open interval. What about the closed interval? We could have a situation where it may converge on -1 to 1, the half open interval, or we could have it converge from the other half open interval, like that, or it could converge on the closed interval. We don't know. We need to check the endpoints to see what happens. Now, for the geometric series, we know that it only converges on the open interval. We've already done that. And the way that I got the interval is simply by rewriting this. If I drop the absolute value, what I get is -1 is less than x, which is less than 1. And that gives me that open interval. Now, I want to consider again that geometric series, which we know converges for the absolute value of x less than 1. But again, how do we know that? And the way that we actually truly know it is we apply the ratio test. And remember, the ratio test takes a look at the limit absolute value of the consecutive terms. So what I want to do here is I have the sum, n equals 0 to infinity of x to the n, which, by the way, is equivalent to saying the sum, n equals 1 to infinity of x to the n minus 1. Those are identical. So what I want to do is take a look at the limit as n goes to infinity of the absolute value of x to the n plus 1 over x to the n I'm using that form. That is equal to the limit as n goes to infinity. If I simply do the algebra and reduce this, I get the absolute value of x, which is equal to the absolute value of x. There are no n's involved in this term. And in order to converge, we know from the ratio test, we know this must be less than 1. So that's how we know that it will actually converge. If we check the endpoints, first of all, I'm going to check for x equals -1. I'm looking at, well, actually I should write this interval. This gives me -1 to 1. So I'm going to look specifically at this endpoint and see if I can close it up. We already know we can't because we've addressed that before. But if I do, for x equals -1, we have the sum n equals 0 to infinity of -1 to the n, which is equal to 1 minus 1 plus 1 minus 1 plus 1, yada, yada, yada. We've talked quite a bit about that particular series. That will diverge. So I want to check also for x equals 1. And in that case, what we have is the sum n equals 0 to infinity of 1 to the n. That equals 1 plus 1 plus 1 plus 1 plus 1 on out. That will also diverge because that goes to infinity. So we just confirmed that both endpoints diverge. So I know now that my radius of convergence is going to be 1, and the interval of convergence will be from -1 to 1. All right, find the interval and radius of convergence for this particular series, which is the sum n equals 0 to infinity of x to the n over n factorial. I'm going to use, again, the ratio test. I'm going to take a look at the limit as n goes to infinity, absolute value of x to the n plus 1 over n plus 1 factorial times n factorial over x to the n. Remember, that's the same as dividing. I just multiply by the reciprocal. Well, I'm going to rewrite this because sometimes reordering things makes it a little bit easier to see what's going on. This is actually x to the n plus 1 over x to the n times n factorial over n plus 1 factorial. This will reduce, just a little bit of algebra here. So this is the same as the limit as n goes to infinity. X to the n plus 1 over x to the n is actually the same as just x. Times n factorial over n plus 1 factorial. That's the same as 1 over n plus 1. Well, that limit is 0. So because it's 0, there are no x's involved. Therefore, this will converge for all x, assuming, of course, x is a real number. That means that the radius of convergence is infinite, and the interval of convergence is also infinite. All right, take a look at one last example. I want to find the interval, and I didn't say it, but I should add also the radius of convergence for the sum n equals 0 to infinity of x minus 2, quantity raised to the n plus 1, divided by n plus 1 times the quantity 3 raised to the n plus 1. Well, right away, I'm going to go to the ratio test. And I'm going to take a look at the limit as n goes to infinity of the absolute value of x minus 2 raised to the n plus 1 plus 1 divided by n plus 1 plus 1 times 3 to the n plus 1 plus 1 times n plus 1, 3 to the n plus 1 over x minus 2 to the n plus 1. Absolute value of all of that. Okay, again, I'm going to rewrite this, rearrange a little bit, make life a little bit easier. That's the limit as n goes to infinity of absolute value of x minus 2 to the n plus 2, obviously, divided by x minus 2 to the n plus 1 times n plus 1 over n plus 2 times 3 to the n plus 1 over 3 to the n plus 2. Absolute value of all that. Well, that's going to be equal to the limit as n goes to infinity. Let's see, x minus 2 to the n plus 2 over x minus 2 to the n plus 1, that's just absolute value of x minus 2. Let's deal with this. 3 to the n plus 1 over 3 to the n plus 2, that's just 1 over 3, so I'll just divide this by 3. And then, of course, times n plus 1 over n plus 2. Now, in the limit, this will go to 1. So this is actually equal to the absolute value of x minus 2 over 3, which I know has to be less than 1. That tells me the absolute value of x minus 2 has to be less than 3. So right there, I know that the radius of convergence is 3. Now I need to expand that out, solve it. I'll have, see, negative 3 is less than the absolute value of x minus, whoops. The whole point there is I could drop the absolute value. So negative 3 is less than x minus 2, which is less than 3. Which implies, if I add 2 to all three components here, I'll have negative 1 is less than x, which is less than 5. So my interval, which I know to converge, is the open interval negative 1 to 5. But I need to check the endpoints. So the first one I'm going to check is take a look at this negative 1. So for x equals negative 1, what we have is the sum, n equals 0 to infinity, of negative 3 to the n plus 1 over n plus 1 times 3 to the n plus 1. Well, I'm going to rewrite this just a little bit. This is sum n equals 0 to infinity, negative 1 to the n plus 1 times 3 to the n plus 1 over n plus 1 times 3 to the n plus 1. Well, the 3 is going to cancel out. And this is the alternating harmonic series. So I know to converge. So I know now I'll have at least a half open interval because the negative 1 will be included. So now I need to check for x equals 5, in which case we have the sum n equals 0 to infinity of 3 to the n plus 1 over n plus 1 times 3 to the n plus 1. Obviously those are going to cancel out. And I would get the sum n equals 0 to infinity of 1 over n plus 1. This is the harmonic series, which I know will diverge. So that tells me that my actual radius of convergence is in fact 3. That doesn't change when I include or exclude the endpoints. But the interval of convergence is negative 1 to 5, that half open interval.